A black hole is an eerie place where those laws of physics we studied at school stop working. If a massive star runs out of its fuel, it sometimes becomes super dense and buckles under its own weight, collapsing inward and bringing space-time along. As a result, the gravitational field of this new object gets so strong that nothing can escape it, not even light. That's how a black hole is born. The black holes closest to our planet are called Gaia BH1 and Gaia BH2. They were discovered thanks to the data collected by the European Space Agency's Gaia spacecraft, hence their names. Both are about 9 to 10 times more massive than our Sun and are located a mere 1,560 and 3,800 light-years away, respectively. In cosmic terms, they're situated in Earth's backyard. And there's something seriously wrong about these black holes. So, should you pack your emergency bag? Let's find out. The remarkably close black holes are likely to represent a previously unknown category of these mysterious objects. What sets them apart from others is that they're orbited by stars at much greater distances than scientists have observed previously in other black hole companion star pairings. Normal black hole companion star systems are known as X-ray binaries. They are usually bright in radio and high-energy X-ray emissions. They swallow matter and emit powerful bursts of energy, which makes them pretty easy to spot. Now, why did it take astronomers so long to spot these massive black holes residing right inside our home Milky Way galaxy? All because they're almost invisible. In the past, astronomers spotted black holes by looking for the remnants of their meals. The thing is that when a star or even a cloud of interstellar gas is pulled into a black hole, it leaves behind a trail of electromagnetic radiation. And scientists use it to detect the presence of a black hole. But unlike other holes discovered before, Gaia BH1 and BH2 are pitch black. They don't seem to be snacking on anything at the moment. This makes them inactive, or dormant. So astronomers had to use another method. They tracked the movement of two companion stars orbiting these cosmic monsters. The stars, similar to our Sun, wobbled a bit while traveling through space. To researchers, it was a sign that something with a lot of gravity, like another star, was tugging on them. Interestingly, when they examined the area with the help of telescopes, they didn't find anything emitting radiation. So the whole situation only made sense if there was a black hole involved in the process. Luckily, Gaia is perfect for spotting invisible black holes. Thanks to its state-of-the-art equipment, it can accurately measure the motion and position of billions of stars. No other instrument is capable of such precision. Gaia's observations were backed up by the data received later by other observatories. For instance, NASA's Chandra X-ray Observatory, as well as the South African Meerkat Radio Telescope, revealed no visible light coming from Gaia BH2. So even though they detected nothing, it was still valuable information. It told astronomers a lot about the environment around the black hole. A lot of particles are coming towards it from the companion star in the form of stellar wind. But the researchers didn't spot any radio light. It means that the black hole doesn't have much of an appetite, and not many particles cross its event horizon, or the point of no return. Unfortunately, it's still unclear why that is. Anyway, should we be worried about those mysterious black holes lurking in the darkness of space so close to our planet? I've got some good news. There's absolutely no reason to worry. First of all, these black holes are sleeping at the moment. And it doesn't look like they're going to wake up anytime soon. Secondly, they're still too far away to affect our life. And it's not like black holes know how to travel.
How about going deep into the past? To the times before humans existed, before the infamous asteroid hit Earth, wiping off 3/4 of life forms on the planet, even before the sun ignited or galaxies appeared in the darkness of the cosmos. So, before light could even shine, there was the Big Bang. It happened 13.8 billion years ago. But what was before that? Some scientists are sure that there was no before. Time started ticking as soon as the Big Bang occurred. We're unlikely to ever figure out what reality was like before that, if any. This is beyond human understanding, but there are those who disagree. Some unconventional scientists theorize that just a moment before the Big Bang, all the energy and mass of the nascent universe could be compacted into an insanely dense but still finite speck. Let's imagine it as a seed of a new universe. And this seed, a chunk of essential material, compressed and hidden in a protective shell, was created nowhere else but inside a black hole. Black holes spin incredibly fast, probably close to the speed of light. Such a spin can give the tightly compacted seed a ginormous amount of torsion. So the seed isn't just tiny and extra heavy, it's also compressed and twisted, which means that it can suddenly unspring with a big bang. Now, let's say you add up the energy and mass of all the particles the visible universe contains. And then you try to figure out the answer to the following question. How big could the event horizon of a black hole with the same mass be? The event horizon is the point of no return. Once you cross this invisible line, there's no way back, even for light. But let's get back to our question. Shockingly, such an event horizon would be very close in size to the actual horizon of the observable universe. There's also this idea that became well known thanks to Stephen Hawking. According to it, every time a black hole appears in our universe, it probably gives rise to a baby universe. But you would only be able to visit such a universe if you crossed the event horizon and plunged inside the black hole. And as you know, once you did it, you wouldn't be able to return. In other words, right now, we might be living in a baby universe. But if some outsider is observing us at the moment, our world looks to them like a regular black hole. So in short, there could be a very old mother universe that forged a seed inside a black hole. This seed had its big bounce all those billions of years ago, and as a result, our universe came into existence. But even though since then it has kept growing and expanding, we might still be hidden behind the event horizon of our home black hole. There's also another idea. According to string theory, there's a multiverse of universes. Imagine our universe as a soap bubble. This bubble keeps expanding, and we live on its surface. String theory claims that our bubble isn't unique. There might be other bubbles out there, and all these bubbles move around, collide, sprout, or bud baby bubbles. In short, live their life. If we follow this theory, we might suppose that black holes are one-way doors between universes. And if you accidentally tumbled down the black hole in our home Milky Way galaxy, you'd end up in another universe. Or rather, not you, but what's left of you after falling through the insane weirdness of the black hole. In this case, this second universe wouldn't be inside ours. It would exist separately, and the black hole would merely be the link connecting them, like a shared route between two aspen trees. Whatever the truth, the danger is still there, lurking in the shadows. What if the black hole we live in decides to collapse? What if it pulls us deeper inside? Or if our world is just a bubble among trillions of other bubbles? What if it bursts one day?
You're dashing through space in your state-of-the-art spaceship. It's the year 3023, and by now people have figured out how to travel at the speed of light. Your equipment works properly and doesn't show anything out of the ordinary, but suddenly, you feel it. An overwhelming pull. You check the region of space you're traveling through and see something that makes your hair stand on end. You're heading straight into the heart of a supermassive black hole. You didn't notice it before because these space monsters have such an immense gravitational pull that even light can't escape their clutches. So they're literally black. What happens next is hard to describe. Time and space are getting warped, and you can't understand what's happening to you and your spaceship. Normally, your story would finish here. But for some unfathomable reason, you survive and are spewed with great force in... Actually, you have no idea where you are. But what you do understand is that a black hole wouldn't let you go so easily. So, what on earth is this thing you've just left? Could it be a white hole? This is a theoretical cosmic region functioning in the opposite way to a black hole. While nothing can escape a black hole, nothing can enter a white hole. You turn around. The white hole, if it really is a white hole, looks exactly like a black one. Your equipment shows that it has a certain mass. It also seems to be spinning. You also spot a faint disk of dust and gas gathered around the event horizon, a bubble boundary separating the insides of the white hole from the rest of the universe. Then, you witness something incredible. A belch. That's when you finally realize you might be the first person to find a real white hole. While the event horizon of a black hole prevents stuff from escaping, in white holes, this boundary doesn't let things enter it. And if we assume that black holes don't destroy any information that gets inside, there must be a way for this information to come back out. So can this something helping information escape be a white hole? So far, white holes are only a theory. You can imagine them as black holes in reverse. Another question is how white holes might form. One of the most popular theories claims that a white hole could be a black hole that has almost collapsed in on itself and then exploded outward again. No one has seen it, obviously. But inside a black hole, there might be a long tube. It gets longer and narrower until it reaches the point in which it gets so narrow that quantum effects make it bounce back. And then this super long and super narrow tube starts getting thicker and wider again. And that's how a white hole is born. But what could make a black hole want to turn itself inside out? Quantum mechanics states that many things we perceive as continuous are actually granular. For example, let's take light. It's not a continuous wave, it's made up of photons. So if we apply quantum mechanics to space itself, we'll find out that the cosmos is granular too. It means a black hole can't squeeze stuff down to infinity. At some point it will reach its minimum size, and this matter, or whatever is falling down the black hole, will have to stop and bounce back, giving birth to a white hole. What matter might a white hole spit out? Some experts think it could be ordinary electromagnetic radiation. It'd probably be unrecognizable from what originally fell into the black hole, since things get horrendously squashed after entering black holes. Black holes are known to absorb everything, matter and energy. As for white holes, they would expel everything, almost like anti-gravity, endlessly ejecting material. To discover a white hole, we'd probably need to look for a place where matter would be ejected with enormous force and a lot of energy. The main question of all time goes like this: what was there before the Big Bang? The most common theory claims that about 13.7 billion years ago, before this incredible rapid expansion occurred, the universe existed as a singularity. It was a point tinier than a subatomic particle. At least, that's what the Big Bang theory tells us. Okay, but what was before that? This question has been bothering the minds of the greatest cosmologists for at least 1,600 years. For example, 4th century theologian St. Augustine was trying to figure out the answer to the question of what had existed before the universe was created. He made a conclusion that the phrase, "in the beginning," mentioned in the Bible, implied that nothing had existed before that. He also believed that time and the universe had been created simultaneously. The ancient Greeks were also bothered by the same question and kept debating the origin of time. Philosopher and scientist Aristotle, for instance, took the no-beginning side. He thought that nothing could come out of nothing. In other words, to get a universe, you need to have something for this universe to appear from. And since the universe couldn't have gone from nothingness to somethingness, it must have existed forever. That's why time must stretch eternally into the past and future. In the early 20th century, the world got to know about Albert Einstein's theory of general relativity. According to this theory, mass warps time, making it run a bit more slowly for, let's say, a human standing on Earth's surface and a satellite orbiting our planet. Based on Einstein's work, other ideas started to pop up, including the one that stated that the universe started as a singularity and expanded through the Big Bang. Then, quantum physics came into play. It gave birth to a bunch of new theories, which brought forth the questions about the pre-Big Bang universe again. And aren't these ideas fascinating? Some researchers believe that our universe is just an offspring of another much older universe. According to them, the evidence for this theory can be found in the cosmic microwave background, CMB. which is the relic radiation left over from the Big Bang. But let me explain. For the first time, astronomers observed the cosmic microwave background in 1965. At that time, they didn't know it would soon create problems for the Big Bang theory, challenging its ideas and postulates. Now, according to the inflation theory, an extremely rapid expansion of the universe occurred in the very first moments of its existence. This theory accounts for the changes in temperature and density in the CMB. It also claims that these fluctuations should be uniform. But recent mapping results show that the universe is actually lopsided. More fluctuations occur in some areas than in others. This makes some scientists believe that our universe bubbled off a parent universe. There's also a chaotic inflation theory, which takes this concept even further. It believes in an endless progression of bubbles, each eventually becoming a universe. And each of these appearing universes gives birth to even more bubbles, which results in an immeasurable multiverse. There are other models too. Some of them revolve around the pre-Big Bang singularity and black holes. If we think of these space monsters as cosmic trash compactors, they might end up being the main candidates for primordial compression. And our rapidly expanding universe could be a white hole output from a black hole dwelling in another universe. A white hole is a hypothetical object that acts in the opposite way to a black hole. Instead of pulling everything inside, it constantly gives off energy and matter. There's also the Big Bounce theory. Its main idea is that instead of going through one Big Bang, the universe expands and contracts in a cycle, bouncing back every time it shrinks to a certain size. Each cycle, therefore, begins with a tiny, smooth universe that gradually grows, becoming more warped with time. And eventually, it starts to collapse, smoothing itself out before starting anew. If you liked or disliked our video, put a like or dislikes. Leave comments. Let's discuss the mysteries of the universe together. And now don't leave, the video will continue. Black holes are terrifyingly dense space objects, pulling inside everything that comes too close. Nothing can escape their clutches, even a beam of light. At the same time, black holes are some of the most mysterious objects in the universe. According to their mass, black holes are usually divided into three categories. Stellar black holes have a mass from a few to hundreds of times the mass of the Sun. Intermediate black holes should range from 100 to hundreds of thousands of times the Sun's mass. Scientists are now actively hunting these missing link black mysteries. But the real behemoths of the cosmos are supermassive black holes. They have hundreds of thousands to billions of times the mass of our Sun. Most supermassive black holes lie in the centers of their home galaxies. You can probably say that they sit in the gravitational driving seat. Meanwhile, hundreds of billions of stars, planets, and moons orbit them. Let's have a look at the biggest black holes astronomers have found so far. NGC 6166 is a monster that has grown to have a mass of 30 billion solar masses. It's actually an elliptical galaxy that has an active nucleus in the center. It's also one of the most luminous sources of X-rays. The galaxy's supermassive black hole powers two symmetric radio jets in the opposite direction, which is the result of the infall of gas into its center. Another peculiar thing about NGC 6166 is that it shows a blue shift, which means it's moving toward us. The next supermassive black hole is located in the constellation of Draco, approximately 10.4 gigalight years from us. The mass of this supergiant is more than 30 billion solar masses. Besides being incredibly massive, the black hole is also really big. If it replaced our Sun, the diameter of this hole would extend to the orbit of Pluto. This S5 Thera 1481 is one of the most interesting black holes on our list. It has a mass of 40 billion solar masses and is actually a blazar, the most energetic of all quasars, which are super bright distant objects. The blazar's luminosity is 300 trillion times that of the Sun and more than 25,000 times as great as the luminosity of all 100 to 400 billion stars of the Milky Way galaxy combined. But since the distance to this quasar is about 12.1 billion light-years, we can't see it directly. But we know that the central black hole of the quasar consumes huge amounts of matter, about 4,000 solar masses of material every year. IC 1101 is a supergiant elliptical galaxy. It's the most massive known galaxy so far. Since this galaxy is elliptical, it isn't filled with gas. That's why the star formation in that region is very low. As for the black hole at the center of IC 1101, it has a mass of 40 to 100 billion solar masses and emits clear radio signals. Recently, astronomers have discovered a gravitational space wonder that is swollen to really unimaginable proportions. The black hole I'm talking about is TON 618, and it's a mind-boggling 66 billion solar masses. The thing is so massive that astronomers had to think of a new term to describe it. They came up with an ultramassive black hole. Imagine gathering all the stars in our home Milky Way galaxy and squishing the matter they're made of into one black hole, and it still won't be enough to create a TON 618. If this monster of a black hole replaced the Sun, its radius would be more than 40 times the size of Neptune's orbit. You probably know that black holes are made of matter packed together as densely as possible. And still, it doesn't mean that black holes are some kind of space predator, roaming galaxies and munching on everything they come across. TON 618 still has a whole galaxy filled with stars and other stuff happily orbiting it without getting pulled inside. What I want to say is that the perception of black holes as giant vacuum cleaners is wrong. In reality, it's incredibly hard to grow a black hole. Try to do it and you'll see.
Hey, it's quiz time! Ready to strain your brain with these mind-bending true or false trivia questions? Let's get to it then! Spider silk was once used to make guitar strings. This is false. Spider silk was never used to make guitar strings, but it has been used to make violin strings. This is because spider silk can produce unique and thrilling sounds, making them a useful resource for building musical instruments. Astronauts crave spicy food in space. True! In space, most astronauts will lose their sense of smell, and our sense of smell is usually what makes us perceive the taste of food. Because of that, many astronauts begin to crave fiery sauces, such as Tabasco sauce, to make up for the lack of flavor in their food. Astronauts see the sun as yellow while they are in space. This is false. While in space, astronauts see the sun as white instead of yellow. As Earthlings, we perceive the sun as yellow due to a distortion caused by the Earth's atmosphere. But since there's no atmosphere in space, the sun appears like a huge white glowing sphere. A coconut is a nut. False. Coconut is actually a one-seeded drupe, i.e., a fruit with a hard covering enclosing as a seed. In case you're wondering, peaches and olives are also drupes. Some lizards have green blood. This is actually true. The green-blooded skink, a lizard living in the country of Papua New Guinea, has high levels of a greenish pigment called biliverdin, which gives its blood a green color. Sound travels faster through steel than air. You bet it's true. Sound travels about 17 times faster through steel than through air. This happens because molecules in a solid material are packed closer together than they are in a liquid or gas, which allows sound waves to pass more easily through them. In England, black cats are considered bad luck. False. Although black cats are considered symbols of bad luck in many places, they're actually considered good luck in England. NASCAR race car drivers can lose up to 20 pounds of sweat in a single race. This is false. Still, NASCAR race drivers can lose up to 10 pounds of sweat in just one race. This happens due to a variety of things, including the high temperatures outside, heavy uniforms, and accumulated heat inside the cars. Odontophobia is the fear of teeth. Yes, it is. People with odontophobia, also known as dentophobia or dental fear, do not enjoy going to the dentist. A referee at a FIFA World Cup soccer tournament runs about 30 miles during an average game. False. Referees sure run a lot, but they run an average of 12 miles per game. The world's largest desert, the Sahara in Africa, is about the size of the Amazon rainforest in Latin America. False. The Sahara is enormous, but its 3.3 million square miles are about the size of Australia, not the Amazon. Geckos usually eat their skin as soon as they shed it. True. Geckos love to munch on their skin, but they can't live on that alone, of course. They also eat bugs. Yum! Ostriches are one of the few species of bird that cannot fly. This is absolutely true. Ostriches have wings, but they can't fly. However, ostriches are fleet, strong runners. They can sprint up to 43 miles an hour and run over 31 miles an hour. They may use their wings as rudders to help them change direction while running. The first macaroni and cheese recipe ever to be registered was back in the 13th century. True! It's hard to believe, but macaroni and cheese is believed to be a traditional dish. Foodie historians found an Italian cookbook from the 13th century with what they believe to be an early mac and cheese recipe. The black box in a plane is black. As confusing as this may sound, this is false. Airplane boxes are actually orange. The so-called black boxes document everything that happens on board a plane. In case of an accident, they need to be a bright color in order to make them easier to find. Haven't you heard? Orange is the new black. M&M stands for Mars and Murray. Yup, this is true. These are the last names of the candy's co-creators. A is the most common letter used in the English language. False. The most common letter used in English is E. It appears in about 11% of all English words according to the Oxford dictionaries. A lion's roar can be heard up to 5 miles away. This is true. Monaco is the smallest country in the world. Nope, false. The smallest country in the world is Vatican City in Rome, with a total of 17 square kilometers. Madonna's real name is Madonna. True, Madonna was born Madonna Louise Ciccone. Coffee is made from berries. This is true. The liquid coffee we drink goes through a long process. Originally, farmers picked out coffee berries, then they are processed and dried. The beans are then roasted and ground and finally ready to be consumed. An octopus has 3 hearts. True. An octopus has 1 main systemic heart to pump blood around its body. The 2 additional hearts are responsible for pumping blood over each of its gills. Venus is the hottest planet in the solar system. True. Although Mercury is closer to the Sun, it has no atmosphere, so it is subject to great temperature fluctuations. But Venus has an average surface temperature of around 850 degrees Fahrenheit, making it the hottest planet in our system. Bananas are curved because they grow upwards toward the Sun. True. A process called negative geotropism means the fruit grows upwards to break through the canopy. Fish can blink. This is false. It would be pretty cute if they could, though. Hot and cold water sound the same when poured. False. Weird fact, but they sound different due to the fact that hot water has a higher viscosity than cold water. Denmark has twice as many pigs as they have people living there. True. Denmark has a human population of more than 5 million, but its pig population is twice as big as that. No one has ever traveled around the world in a hot air balloon. This is false. In March 1999, Brian Jones and Bertrand Piccard made the first non-stop flight around the world in a balloon. Their journey began in Switzerland and finished over Africa. It took them just 20 days. Scientists developed a fork that measures how fast you eat your food. Yup, it's pretty true. The inventors hope that people will use this fork in order to learn to eat more slowly. The acronym NASA stands for the National Astronomy and Space Administration. False. NASA stands for National Aeronautics and Space Administration. Astronauts grow about 6 inches in space. False. 6 inches is a lot. Usually, astronauts can grow between 1 and 2 inches when they're traveling through space. This happens due to the lack of gravity, which makes the human spine stretch out, causing astronauts to grow a little bit. There is a scientific reason why people cringe when they listen to nails scraping a chalkboard. True. Fingernails scraping a chalkboard produce a similar sound frequency to those of a chimpanzee's warning call. So the sense of distress humans might feel when fingernails scrape could be a sign that our fundamental primate danger sensors have been triggered. Medieval bakers used to color their flour white with the help of chalk. This is true. Back in the day, white bread was a sign of wealth and was sold at higher prices. So some bakers used to color their flours with chalk in order to sell whiter bread.
You must have heard that humans were supposed to fly to Mars within the next 10 to 20 years, but now the mission seems to be at risk. A new study has revealed the dramatic effects that such a journey can have on the human body, and because of that, the entire plan is now at risk. Samples from over 40 missions, which involve both mice and humans, have shown that the conditions in space are likely to have an even more negative influence on our bodies than we thought. Both NASA and SpaceX are planning to send crewed missions to Mars in the coming decades, but new findings might put an end to these projects. Researchers at University College London have discovered that microgravity and galactic radiation in space cause serious health risks, and they become more and more pressing the longer someone is exposed to these conditions. Surprisingly, the body part at the highest risk is the kidneys. The research has shown that after less than a month in space, some parts of the kidneys show visible signs of shrinking. So before we go all the way to Mars, we'll need to develop measures to protect the kidneys and other parts of the body. This will allow astronauts who will take part of this mission to avoid irreversible damage to their health, which in turn means that future missions to Mars haven't been completely ruled out yet. The author of the study, Dr. Keith Sue, mentioned that they already knew about the issues that astronauts had after short space missions, like kidney stones for example, but they still don't know why such problems occur or what is going to happen to astronauts on much longer space flights, such as the planned mission to Mars. If they don't manage to develop new methods to protect the kidneys, astronauts who will eventually reach the Red Planet might need serious kidney treatment already on their way back. Unfortunately, the effects of radiation damage on kidneys appear pretty late. By the time they become apparent, it might be too late to prevent a kidney failure. This can be catastrophic, not only for the astronauts, but also for the entire mission's chances of success. Meanwhile, an astronaut on Mars is likely to receive up to 700 more daily radiation doses than those we get on our home planet. The Earth's magnetic field and atmosphere protect people from the non-stop bombardment of cosmic rays. These energetic particles travel close to the speed of light and can easily penetrate the human body. In space, astronauts aren't protected against this radiation as effectively as on Earth, which can increase the risk of many serious health issues during long missions. Damage to the human body can extend to the brain, heart, eyes, and central nervous system. Physicists studying cosmic radiation explain that one day in space is equivalent to the amount of radiation one receives on Earth for a whole year. Moreover, most of the changes in the genes of the astronauts are likely to be the result of radiation exposure. That's what a recent NASA's twin study claims. It has shown DNA damage in astronaut Scott Kelly compared to his identical twin and fellow astronaut Mark Kelly, who remained on our planet. Another source of space radiation are the unpredictable solar particle events. They deliver high doses of radiation in short periods of time, which can lead to radiation sickness if astronauts don't take special protective measures. Even space flights orbiting close to the Earth, including the International Space Station, have highly adverse health effects. These days, research communities are focused on musculoskeletal, neurological, ocular, and cardiovascular degeneration, and these issues can appear as soon as a few weeks into a mission. At the same time, the effects of low Earth orbit flights are less clear when we talk about other organs. More research is definitely needed.
It is assumed that there is a supermassive black hole at the center of every galaxy in our universe. These space monsters have been discovered in the centers of many galaxies, and our Milky Way is no exception. There is Sagittarius A at its center, a supermassive black hole surrounded by a hot, radio-emitting, accreting gas cloud. To accrete means to absorb matter from the surrounding space under the influence of gravitational forces. In the case of black holes, the attraction is incredibly strong. As a result, the radiation surrounding them is also immensely powerful. Observations made by the Event Horizon Telescope in 2022 made it possible to simulate this substance in our galaxy. From these observations, astronomers were able to estimate the mass of the black hole. It turned out to be 1 million solar masses, which is about 1 million times less than the mass of the entire Milky Way galaxy. So, 1/1,000,000th of the mass of our galaxy is that supermassive black hole at its center. Such a ratio of the mass of the entire galaxy to the mass of the black hole at its center is characteristic of many observations. Moreover, the value of this ratio is reproduced within the framework of modern models. Now, let's discuss two hypotheses for the formation of supermassive black holes. The first model speaks about the creation of small seeds that describe the gradual increase in the mass of a black hole, the accretion of matter into a stellar mass black hole. The second model suggests that supermassive black holes form when large gas clouds collapse. In this case, the collapse occurs bypassing the stage of a supernova explosion, in which the explosion would scatter most of the mass, preventing the formation of a supermassive black hole. In any case, conceptually, such a process can be described this way. There's matter in some compact area, which is the seed for the growth and development of a black hole. Black holes accrete matter around them and their mass increases. It is important that the evolution of black holes is a temporary process that scientists want to study in dynamics. But how can one see evolution that takes place over millions or even billions of years? Unfortunately, or fortunately, light from a distant galaxy takes time to reach us. That's why if we look at very distant objects, we will see them as they were in the past due to the propagation delay of light. But to look far into the past, one needs to look at very distant objects. The light from them is very difficult to observe experimentally. The good news is that with the launch of the ultra-precise James Webb Space Telescope, scientists can study even faint signals from galaxies that formed when the universe was about 1 billion years old. That is, looking back almost 14 billion years. One of the most surprising results obtained from James Webb is the discovery of a lot of galaxies within 2 billions of years of life of the universe. These galaxies have active galactic nuclei faint, compact regions at the centers of galaxies, emitting large amounts of energy. Here, the Space Telescope shows its power. These active galactic nuclei have luminosity that are thousands of times lower than the luminosity of quasars detected in ground-based studies. They appear red because they are dusty. The dust obscures black holes and reddens the colors. So they're called little red dots. What is very important, their masses lie between 10 and 100 million solar masses. Surprisingly, using very advanced analysis methods, scientists can estimate the mass of a black hole at the center of a little red dot. It turns out that it reaches millions of solar masses. It means that the mass of a black hole at the center of such a little red dot is only several orders of magnitude less than the mass of an entire galaxy. I'll remind you that the supermassive hole at the center of our galaxy is millions of times smaller than the mass of the entire universe. Thus, the ratio of the mass of supermassive black holes at the centers of such galaxies to the mass of the entire galaxy is phenomenally large. But explaining this fact will be a difficult problem for current models of black hole evolution. One of the hypotheses that scientists are now working on is that it's not a black hole that forms from a seed at the center of a galaxy, as we discussed earlier. It's a galaxy that forms around the already created black hole. Such black holes are called primordial black holes. This is a hypothetical type of black hole that was formed not due to the gravitational collapse of a large star, but in superdense matter during the initial expansion of the universe. If it turns out that these primordial black holes do exist, it will open up a new window for dark matter models. But this is a topic for another video. Recently, an international team of astronomers has used the James Webb Space Telescope to find evidence for an ongoing merger of two galaxies and their massive black holes, and it happened when the universe was a mere 740 million years old. The double black hole system is known as ZS7. This is the most distant detection of a black hole merger ever. Plus, it's the first instance of such a phenomenon detected so early in the universe. But let's look into the details. Astronomers have been locating different supermassive black holes with masses of millions to billions of times the mass of the Sun, situated in the most massive galaxies in the local universe, including our home Milky Way galaxy. Those giant black holes most likely had an immense impact on the evolution of the galaxies where they dwell. At the same time, scientists don't fully understand how those objects got to be so massive. The discovery of such monstrous, fully formed black holes means that their growth occurred very quickly and very early. Massive black holes that are actively accreting matter have special features that allow astronomers to detect them. These features are usually not visible from the ground, but can be observed with the help of James Webb. So, researchers found evidence for very dense gas clouds with rapid motions close to the resulting giant black hole. Plus, they detected hot and highly ionized gas, illuminated by energetic radiation, like the one typically produced by black holes in their accretion periods. With the incredible sharpness of the telescope's imaging capabilities, scientists also managed to spatially separate the two black holes. One of these holes has a mass that is 50 million times the mass of the Sun. The mass of the other black hole is likely to be similar, but it's much more difficult to measure it since this second hole is surrounded by a thick cloud of gas. These findings suggest that mergers are a crucial way through which black holes can grow extremely fast, and they could do it already at cosmic dawn. After analyzing other Webb's findings of active massive black holes in the distant universe, researchers have come to the conclusion that massive black holes have been influencing the evolution of galaxies from the very beginning. Once the two black holes merge completely, they will also generate gravitational waves. Such events are supposed to be detected by the next generation of gravitational wave observatories, such as the upcoming Laser Interferometer Space Antenna, aka LISA, mission. It has been recently approved by the European Space Agency. This mission will be the first space-based observatory dedicated to studying gravitational waves. The results we get from James Webb tell us that lighter systems detectable by LISA might be more frequent than we used to think. It will likely make researchers adjust their models for LISA rates in a similar mass range. Currently, astronomers are planning to study in detail the relationship between massive black holes and their host galaxies in the first billion years. An important part of this program is systematic search for and characterization of black hole mergers. It will help us determine the rate at which black hole merging occurs in the early universe. Plus, with the help of this research, we can figure out the rate at which gravitational waves have been produced from the dawn of time.
Hey, ever wondered what's bigger than infinity? Infinity plus one? Nope. It's not even infinity times infinity. But indeed, there are situations in which one infinity can be bigger than another infinity. I hope I haven't confused you yet. First of all, we've got set theory. That's when you take a group of something and put it into a defined set. For example, 5 pencils. But it can actually be anything. It doesn't matter. What matters is there is stuff in the set. Okay, you might be wondering, how can it help me understand infinity? Let's try to somehow define the size of the set. Well, it's easy to understand that the size of a set of finite elements is simply the number of these elements. But how should we think about the size of infinite sets? Oh, let me introduce correspondence to you. This is a concept in set theory that functions by relating one individual object in one set to another individual object in another set. These individual objects can be some items or just numbers. The main thing is that each item in one set can be compared to an item in another set. For example, 2 pencils to 2, 4 pencils to 4, and so on. We cannot compare the sizes of infinite sets, but we can define correspondence between elements. And if 2 given sets have a one-to-one correspondence between their elements, then these 2 sets have the same cardinality. Roughly speaking, the word cardinality means numbers of elements. If the cardinality of some infinite set is equal to the cardinality of the natural numbers 1, 2, 3, 4, 5, 6, we call the power of this set Aleph 0. Let's stop here for a moment and do some math. Do you still remember our main question? Right. How can one type of infinity be smaller than another? But what if we use 2 different sets of counting numbers, which are also called natural, and imagine that both these sets extend forever? Set A, 0, 1, 2, 3, 4, 5. Set B, 1, 2, 3, 4, 5, 6. As you see, set B starts one number higher than set A. But we have one-to-one correspondence between sets. It means that they represent equal types of infinities. In other words, each number in set A corresponds to another number in set B that is one value higher 0, 1, 1, 2, 2, 3, etc. Now this is the smallest type of infinity, the very Aleph null. Okay, another question remains. Why isn't infinity, let it be Aleph null plus 1, bigger than good old Aleph null? Well, here's another example. This person is a cyclist. We take his bike, use it as a +1, and put it in set A. Now, our sets look like this. Set A, bike, 1, 2, 3, 4, 5. Set B, 1, 2, 3, 4, 5, 6. Following the logic, we match the bike to 1, 1 to 3, 3 to 4, and so on. As you see, it's possible to keep this one-to-one correspondence between the sets, and it can go on forever. It means that infinity and infinity plus 1 indeed have the same cardinality. But wait, it gets even weirder. Picture building a set using only natural numbers ending in 0, 10, 20, 30, etc. Then you compare it to the set with all the natural numbers 0, 1, 2, 3, 4, 5, etc. At first glance, it seems that the second set should be 10 times larger than the first one. But as far as the set theory is concerned, these 2 sets are equal. Amazing, isn't it? Then how can any infinity be bigger than another one? To figure it out, we need to enter the world of real numbers, which are any numbers representing a quantity along a continuous line. It can be 59, 4.335,081 pi, any fraction that comes to your mind, and so on. Imagine 2 points on a line. Between these very finite points, there's an uncountable and infinite set of numbers. Long story short, just trust us that mathematicians can prove that it's impossible to create a one-to-one correspondence between natural numbers and every possible real number. Here you go. With the help of sets, we've found an infinity which is bigger than the infinity Aleph null.
If space were filled with air, the implications would reshape our understanding of the universe and the very nature of space travel, astronomy, and physics. Here are the potential consequences and considerations in such a scenario. Space travel. Complexity. Current spacecraft are designed for a vacuum, where they encounter minimal resistance. In a universe filled with air, space travel would resemble atmospheric flight, requiring spacecraft to be aerodynamic and robust enough to withstand air resistance and the heat generated from friction. Rockets would have wings. Rockets would need significantly more fuel to achieve the same speeds and distances, making space travel more complex and costly. Satellites would need constant propulsion to stay in orbit, as atmospheric drag would cause them to slow down and fall back to Earth. This would make maintaining satellite networks for communication and GPS far more complex and resource-intensive. Breathing in. Space. The presence of air might imply that astronauts could breathe in space, eliminating the need for spacesuits and life support systems. However, if the air's composition and pressure were not suitable for human survival, or if temperatures were extreme due to solar radiation heating the air, protective measures would still be necessary. Thermal dynamics. Space filled with air would have vastly different thermal dynamics. Heat from stars would warm the surrounding air, potentially leading to extreme temperatures across the universe. This could create a range of environments from scorchingly hot near stars to bitterly cold in areas far from stellar heat sources, affecting the habitability of planets and the feasibility of space exploration. Sound propagation. Unlike the current vacuum of space, air would allow sound to travel. This means that the noises of cosmic events such as supernovae or colliding asteroids could be audible. This would not only change the experience of space, but could also provide new data for astronomers to study celestial events. Astronauts on spacewalks might hear the hum of their spacecraft, the whirring of satellites, or even the sounds of solar storms and cosmic events. Altered physics. The fundamental laws of motion and energy would behave differently in a universe filled with air. Spacecraft and objects would lose momentum due to air resistance, and the propagation of electromagnetic waves would be affected, potentially altering how we observe and measure cosmic phenomena. Astronomical observations. The clarity of observations made from within an air-filled space would decrease due to the scattering of light by air particles. This would complicate astronomical research and observation, making it harder to study distant stars, galaxies, and other celestial bodies without the clear view we currently have from Earth and space telescopes. Telescopes would struggle to get clear images due to the scattering of light by the air. Stars and galaxies would appear blurry, and many of the deep space discoveries we've made would be impossible with our current technology. Cosmic radiation shielding. While air could offer some protection against cosmic radiation compared to the vacuum of space, its effectiveness would depend on the air's density and composition. This might not suffice to protect humans and the electronic equipment from the high-energy particles prevalent in space. Orbital mechanics. The presence of air would also affect the orbit of celestial bodies. Planets, asteroids, and comets would experience drag as they moved through space, potentially leading to orbital decay and altering the dynamics of solar systems and galaxies. With air resistance slowing down space debris, Earth might experience more frequent but less intense meteor showers as objects in space burn up in the denser atmosphere at higher altitudes. Evolution of stars and galaxies. The life cycles of stars might be different in a universe filled with air. The processes of star formation, supernovae explosions, and black hole formation would be influenced by the interaction with the surrounding air, possibly leading to different types of astronomical structures and phenomena. Living and working in space would be different in such a universe. The experience of walking on a planet without a spacesuit and hearing the sounds of space would be profound. However, the challenges of dealing with the dynamic and potentially hostile environments created by air and space would necessitate new strategies and technologies for exploration and habitation. In conclusion, an air-filled universe would present a radically different reality from what we know today. The physics of movement, the nature of space exploration, the methods of astronomical observation, and even the sounds and sights of space would be transformed. The challenges would be immense, but the opportunities for discovery and understanding would be equally vast.
Oxygen, as well as the process of breathing, is crucial for our survival. You breathe every minute and every second of your life without even thinking of it. But there's next to no molecular oxygen, which we also know as O2 in space. Interestingly, in 1998, NASA sent to space a satellite whose main goal was to find loads of molecular oxygen. But it never did. Then scientists, worried that something could be wrong with the spacecraft's equipment, aimed it at Earth. And guess what? Right, the instrument showed there was plenty of oxygen there. Now, we know why these life-giving molecules are so rare in space. All because oxygen clings to stardust so tightly that it prevents its atoms from joining together and forming oxygen molecules. That's actually the answer to the intriguing question of why we can't breathe in space. There's simply not enough oxygen there for this process to happen. And even if you went out into open space with your own oxygen inside your lungs, it wouldn't help you. In the low-pressure environment of the cosmos, this air in your lungs would expand incredibly fast, making the lungs burst. So that's what would happen if you went to space and decided to walk around without a spacesuit. But that wouldn't be the only tragic consequence. The oxygen in the rest of your body, for example, in your blood, would also expand, making you balloon up to 2 times your normal size. Luckily, your skin is elastic enough, and it would hold your body together. Then, all the exposed liquid on your body would start to vaporize, making it very uncomfortable for, let's say, your tongue and eyes. Since there would be no air in your lungs, your blood would stop sending oxygen to your brain. That's why you'd pass out in around 15 seconds. A few more dozens of seconds, and the lack of oxygen would lead to tragic consequences. Interestingly, we often imagine outer space as a freezing cold and inhospitable place. We believe that if someone ended up there without a spacesuit, they would immediately freeze into a human popsicle. It's a good thing we're on Earth. You can take a deep breath and subscribe to our channel. In reality, though, the cosmos itself doesn't have temperature. You see, scientifically speaking, temperature is a function of heat energy in a given amount of matter. But here's the catch. Space doesn't have any mass. Plus, heat transfers can't happen in space in the same way as they do on Earth. Conduction and convection, because they simply can't occur without matter. Let's get practical. What does the fact that space basically doesn't have temperature mean for a person without a spacesuit floating in the darkness of the cosmos? Let's imagine there is enough oxygen in space, and this person can breathe. Will it help? In space, thermal radiation, which is the heat from the sun's rays, is the main means of heat transfer. So, if this astronaut without a spacesuit was directly exposed to the sun's radiation, they would feel slightly warm or slightly cold if shaded from sunlight. In the latter case, the person's own body would be radiating away heat. But what if they ended up in deep space, where temperatures drop down to minus 455 degrees Fahrenheit? That's the temperature of the cosmic microwave background, the leftover from the Big Bang, permeating the universe. Our astronaut would still not freeze instantly since heat transfers don't occur very rapidly by radiation alone. But the absence of normal atmospheric pressure, which is the one at Earth's surface, would be a much greater concern. The main problem would be the risk of lung rupture due to air expansion. And there's also something called ebulism. That's when reduced pressure of the environment lowers the boiling temperatures of body fluids. As a result, Liquid water in the bloodstream and soft tissues turns into water vapor. So even if humans could breathe in space, it wouldn't change anything in the grand scheme of things.
The Sun is getting ready to flip as its magnetic poles are reversing. Similar to Earth, the Sun has a magnetic north and a magnetic south. But unlike Earth, the reversing process of the Sun's poles is more frequent and easier to predict. The next flipping is expected to take place this year between April and August. As apocalyptic as it might sound, you don't have to worry. If you're around 30, you've already experienced this phenomenon more than once as the Sun flips every 11 years. You probably didn't notice any changes back then because this process doesn't impact Earth's life so much. But this time, things might be a little different. On Earth, ocean currents are movements that play a crucial role in influencing both climate and weather by distributing heat from the equator to the poles. On the Sun, these currents are more like an ocean of plasma, but they not only transport heat but also carry electromagnetic energy. That happens because the Sun is a huge ball of hot and ionized gases that keep flowing inside its core. By fusing together hydrogen atoms and forming helium, our star releases a massive amount of energy, leading to these very heavy flowing electric currents. And whenever you have currents, you have magnetic fields. It's easier to understand if you think of that classic experiment with a wire and a nail that you probably conducted in elementary school. When electricity flows through a wire, it creates a magnetic field around the wire. So when you connect a wire to a battery and wrap it around a nail, the nail becomes a magnet. This is similar to how electric currents create magnetic fields on the Sun. This whole process, with the help of which the Sun generates its magnetic field, is called a dynamo. We can't observe it directly, but we can see its effects on the Sun's surface. When plasma and magnetism flows become unstable and intense, they manifest as sunspots. You know, those dark areas on the Sun's surface? Much about how the dynamo works remains a mystery. But scientists have learned something important after observing these sunspots for centuries. The dynamo process follows a pattern. About every decade, it reorganizes itself. The Sun's polar magnetic fields get weakened, eventually reaching zero, and then they return, but with the opposite polarity. Back in the 50s, researchers figured out that when sunspots start to ramp up and become more intense, it means the poles are gearing up for a reversal. And over the past few years, solar activity has been off the charts. We're talking about more solar flares, more electromagnetic radiation bursts, and more plasma blobs being ejected into space. It's like we're sitting in the front row at the solar system's most epic fireworks display. In fact, the Sun hasn't been this lively in probably 2 decades. Right now, experts think the polar fields are almost in sync and steadily weakening, inching closer and closer to zero. But we haven't reached the point of reversal yet. Although it might sound like the Sun flips its magnetic poles like clockwork every 11 years, the truth is that it's not as neat as it seems. This path can be bumpy, and some aspects of the phenomenon are still very hard to predict. Take the last solar cycle, for example. The Northern Hemisphere started its magnetic flip back in early June 2012. But then it kinda hit a snag and lingered around the neutral point until late 2014. Meanwhile, in the Southern Hemisphere, things were smoother, with the polarity switching over in mid-2013. This time around, the Sun is actually playing nice. Things seem to be running way smoother this cycle, with the poles transitioning more evenly. But here's the thing, reversal processes are never the same. That's what makes this phenomenon so interesting to observe. But at the same time, it's hard to predict how it'll affect us down here. Here on Earth, we don't have to worry too much about those intense sun explosions happening 93 million miles away. But if, and I emphasize if, a solar storm were to reach our planet, the main threat it would bring would probably be the disruption of communication satellites in space. However, things might be different in this cycle reversal happening in 2024 because the number of satellites has skyrocketed in recent years. For example, Elon Musk's Starlink system alone involves more than 4,000 of them. all these satellites, along with communication and GPS satellites, could be impacted or even destroyed by a powerful solar storm. Although the chances of a powerful solar storm hitting Earth are low, it's not impossible. Back in 1859, during the Carrington event, a storm occurred near the peak of the solar cycle, causing currents to surge through telegraph lines, sparking fires and disrupting messages worldwide. Earth fell silent as telegraph communications failed. Just imagine what a solar storm could do to our vast number of satellites today. It could affect everything we rely on daily, from space-based communication and navigation to weather forecasting services. The ground-level power distribution could also be affected. You can forget about watching YouTube or Brightside, because if such an event occurred today, it would cause an internet apocalypse, sending countless people and businesses offline. There's a prediction that says that if a Carrington-class event happened today, it would result in damages ranging from $0.6 to $2.6 trillion. And I'm talking about the United States alone. Fortunately for us, solar storms as intense as the Carrington event happen only once every 500 years or so. Bad news for communication satellites, but great news for aurora watchers. During the Carrington event, dazzling auroras borealis lit up the sky as polar light shows stretched far beyond their usual ranges. The northern lights were spotted as far south as Cuba and Honolulu, Hawaii, while the southern lights were seen as far north as Santiago, Chile. For many people around the world, this was their first glimpse of the aurora, leaving them obsessed with the unusually bright skies. Some of them thought it was the end of the world, while others began their day early, thinking the sun had risen after hearing birds chirping and seeing the bright skies. Today, we know there's nothing strange about it, considering that the appearance of auroras at lower altitudes is one of the expected effects of the sun's magnetic pole reversal. Typically, these dazzling phenomena are found between 60 and 75 degrees latitude, but during the last magnetic pole reversal in 2013, intense auroras were observed below 50 degrees. Eyewitnesses describe these auroras as blood or deep crimson red, shining so brightly that you could read a newspaper in their light. It's important to study this phenomenon and not to fear it. The inversion of the magnetic poles on the sun is actually a great opportunity for scientists to better understand how our star works. Since many pieces are still missing in the whole dynamo situation, we're still not very good at predicting why some solar cycles are more intense than others, or when exactly a coronal mass ejection will erupt. But being able to predict that is becoming more and more necessary as we venture ourselves into space. The more people are out there beyond Earth, the more exposed they are to these strong solar storms. That's why the scientific community wants to know more precisely when a solar storm can cause damage to spacecraft and space stations. Plus, it would help meteorologists make progress in predicting weather, not only on Earth, but also in space. The whole point is to make space travel safer as the interest in crewed missions to the Moon and Mars grows every year. Another reason why it's important to learn more about the Sun's pole inversion is to better understand how the mysterious interior of the Sun works. That could actually help us figure out the aspects of other stars in the universe and maybe get closer to answering the ultimate question: why are we here?